Good morning. So in the previous video we have seen what is a microcontroller and the block diagram of a microcontroller, then the features of 8051, the block diagram of 8051, and also the pin diagram of 8051. And we also have seen few family chips. I mean, the Intel company has produced many different microcontrollers. Out of those, we have compared the features of 8051, 8052 and 8031. So now in today's class we will see the functional block diagram of 8051. So this is the functional block diagram of 8051. Here we have ALU. First we will see the diagram here. ALU, temporary register 1, temporary register 2. Generally this is the complete CPU processing part, where temporary register 1 and 2 are integrated with this ALU itself. Then I have accumulator. ACC is nothing but your accumulator register. Then the B register. Then under ALU you have PSW, that is program status word. So this can also be called as flag register. Accumulator is of 8-bit, B register is of 8-bit, PSW is also of 8-bit. Now here I have stack pointer. This is the stack pointer. Then there is RAM here and RAM address register is here. Then I have here I have ROM and ROM address register. And beside that, if you come from down, I have DPTR, data pointer, program counter, program counter incrementer, and I have a buffer. So these are the blocks here. After this, here I have in between RAM and ROM I have port 0 and port 2 latches, and above the latches it is connected to port 0 driver and port 2 drivers, where I have all my 8 pins, 8 port IO lines. Here port 0's 8 lines and port 2's 8 lines. So total here 8 and 8, 16 pins are over. Then now coming to this part, here I have interrupt serial port and timer blocks. Timer blocks are nothing but you have timer 0, timer 1, and you have TCON. You have special function registers actually in this block. Okay, interrupt serial port, timer blocks and all. Next here beside this PSW you have timing and control, which is given to this oscillator. The oscillator is connected in this way. Then here you have instruction register, where all the instructions are there for decode. Next here I have two ports, port 1 and port 3 latches. Then you have port 1 and port 3 drivers, from where all your bidirectional pins have come out of these drivers. These are 8 and these are 8. So total above you have this 16 and 16, total 32 pins are completed. Remaining 8 pins, that is from those 2 are VCC and ground. Then here you have for a crystal quartz crystal, here you have XTAL1 and XTAL2. Between these two pins that crystal is connected. Next here you have reset pin, pin number 9, input pin EA and reset. This both are input pins. So inverts, arrow is inverts. Whereas the timing and control, here you have ALE and PSEN. These both are output pins, and EA and PSEN both are active low. So the basic structure of this functional block diagram. Now we will just see about each block. What will each block do in this functional block diagram? So this ALU, temporary register 1, so this is the processing where actually occurs. So what it does is it is capable of performing all the arithmetic and logical operations like addition, subtraction, multiplication, division. Then coming to logical, you have AND operation, OR operation, XOR operation, so etc. In this way I have so many operations where this can perform. Next it can also perform bitwise or as well as bytewise manipulations. Next After this we will move to memory. I have here RAM and ROM, both the memories. So RAM is nothing but your temporary memory and ROM is permanent. So generally in ROM I have my code, the program is written on the ROM. It is the programs are stored in that ROM, whereas in RAM the temporary data is stored on this RAM memory. So next I have is IOports. All this port 0, port 2, port 1 and port 3, all these 4 ports are nothing but input output ports. Okay, they are used for interfacing input output devices like switches, keyboards, LED, LCD, A to D converters, D to A converters, in this way. So from all these 4 ports we can interface the different input output devices or for any other input output operations. Next, the external address and the data buses are formed only by using this port lines. Okay. So now after this we will see we have one serial port for this. Okay, we have a serial port. So the serial port is nothing but, generally before knowing this we have seen that you have 4 ports. These 4 ports are input output bidirectional ports, where you can say the parallel ports as well, because parallelly at a time all 8 bits, the input whatever we give, all 8 bits are gone at a time. Whereas coming to serial port, in this serial communication the data is sent 1 bit at a time. Okay, so the 8051 has one serial port for this serial communication only, and in the 8051 it is nothing but full duplex. So hence transmission and receiving as both are being done simultaneously. Next we have timers and counters. So either that block, that timer can work like a timer or a counter. Okay, timer is nothing but it is used to produce a delay. Okay, some delay. For example, we have a coffee machine. Okay, so while having a coffee machine out in the restaurant, whenever I try to place my coffee cup under that filling space area, wherever I try to put my coffee cup, I'll just give some time delay. Some time I'll be mentioning, some button I'll press, mentioning some time. So whenever I do that, till certain time only that coffee will be filled in the cup. So there is certain time, I'm giving some time is set. After with some delay, if it falls, it will take more time. With less delay it falls, it will take little less time. So by using in such applications we use this. And for example, you can also take your microwave oven. Even in that you have some time delay giving. So whenever you give in such applications we use this. And also the counter is used to count the events. Okay, so in short, timers are used to create some delay between any 2 actions. Okay, whereas counters are used to count the events. These are about timers and counters. And this is timer is of 16 bit. You have 2 timers in 8051, each is of 16 bit size, that is timer 0 and timer 1. Next, here you have our interrupt. Okay, so now interrupt control. It is interrupt is a signal sent by some external device or some internal, okay, to a microcontroller, so that it will request the controller to perform a particular task or a function. Okay, so whenever an interrupt is given from an external device or internal, what happens is the processor takes that interrupt and it says the processor to that so that it should stop the present work whatever the processor is doing. It will stop that present task or work whatever it is doing, and it should perform the task given by the interrupt. First preference, first it should perform the task given by the interrupt. So that is what called as interrupt. So the interrupt control unit transfers the microcontroller attention from one task to another, because previously it was doing some other task, the processor was doing some other task, but whenever I gave some interrupt, okay, whenever there was interrupt occurred, so that time what happens, the whatever the previously doing task will be halted and the presently given task by the interrupt will be done. So that is interrupt. Next, here you have oscillator. So definitely this circuit generates the basic timing clock signal for the operation of a circuit using crystal oscillator. Okay, this oscillator circuit generates a train of pulses at a frequency of a crystal. So in this the machine cycle is a group of 6 states. Okay, 6 states. A state is a basic time period for the microcontroller to fetch an opcode or to fetch an opcode, decode an opcode, execute an opcode. Okay, so this 6 states, it is nothing but the basic time period of a microcontroller. To do what it does in that time period, first it will fetch wherever it is there, the opcode, it will try to fetch that from that storage, it will fetch, then it will decode. Okay, so the whatever the encoded format we sent, okay, that will be decoded into binary. Okay, after that it will execute that operation. Okay, whatever the operation is there, that operation will be executed. Next, you have here you also have SFRs in this block. Okay, so generally you have many SFRs like even A come under the same, because in separate this are being at a place not in internal RAM, they are at separate some special function registers from 80H. So A, B, DPTR, PSW. Okay, DPTR means data pointer, then program status word, then you have interrupt priority, interrupt enable, IP, IE, then TCON, SCON, all such ports, all these come under this SFRs. Okay, from there these are few are byte addressable and few are bit addressable. This timing and control unit, this unit synchronizes all the operations with the clock and generates the control signals for proper functioning. And here you also have instruction register. This also is also an 8-bit register. So whenever the instruction is fetched from a memory, whenever this is fetched from memory, it is loaded into this instruction register. Then it holds the instruction which is to be decoded. In this wherever the memory, I mean I said in a ROM you have all the programs. Codes are written in the form of instructions from an instruction set. So that is been fetched first and it is brought to this IR to decode. So this is the work of this IR. And temporary registers are a part of this ALU, which we already discussed. Then you have accumulator. Yeah, so accumulator is also a 8-bit register. This accumulator is also an 8-bit register. It is used for all arithmetic and logical operations. So whenever you write a program, in that A must be used as a destination for all addition and subtraction operations. So whenever you are writing some instruction, if you are writing some addition operation, add, ADD is the instruction. The format of this operational code is, we'll write an instruction, nothing but that represents the operation first. Then after that I'll write the memory locations where that operation is being implemented, at what place. So that is written in the form of source and destination. So after writing the instruction, first we'll write destination, after destination I'll write source. Okay, so now in the same way, if I wanted to write add A, B, so A is one register and B is one register. So then what will I write? ADD is the instruction for addition in 8051. So I'll write ADD A, B. That means A is the destination, then B is the source, I mean wherever whatever the values are there in it. So whatever the values are there in A and B, those both will be added by processing in 8051, and in the end result will always store in a destination register. Now in this instruction add A comma B, destination is A. Destination register, whatever I have written is A register. So the result will be stored in A register only. So the A register must be used as a destination for all the addition and for all the arithmetic operations. And for logical operations, this can be used as source or destination. It can be source or destination, anything. Next, there are some specific operations like clear, complement, rotate, swap. So for these we must reside in A register only. So we should always take A register only for such operations like clear, complement, rotate and swap. Apart from A, you can't take some other registers. Where it is invalid, it won't take other registers. And there are two more important things while doing a multiplication. Whenever you do a multiplication operation, then after that instruction is been executed, the result whatever you get, if you get whenever you multiply to 8 bits, sometimes you will also get 16 if the numbers are very bigger numbers. So that time you need 16 bit. So 16 bit can't, the result generally you know that in arithmetic operations result will be stored in accumulator because it is a destination register. But in case of the 16 bit number, 16 bit result, only 8 bit it can store. That time in the case of multiplication, A will be having the lower byte of the result and the higher byte will be stored in B register. In that way the result is stored. Whereas in division you have two results, one is remainder and other is quotient. So while dividing, even before the execution, A holds the dividend, okay, 8 bit dividend, and after execution of this division instruction the quotient is stored in A register, whereas in B register remainder will be stored. So is that fine? In accumulator is of 8 bit register. It is used for all arithmetic and logical operations. Then register must be used as a destination register. Then this A register can use few operations like only these operations should be used for A, such like clear, complement, rotate, swapping and all. For logical we can use as a destination or a source. Then for multiplication, after the execution of multiplication the result is stored in A. If it is a bigger number then lower byte will be stored. In division quotient will be stored in A. And B is also 8 bit register, and in multiplication the higher byte will be stored after execution. For division the remainder will be stored in B. Next, see we already discussed about accumulator, B register. Now we will discuss about this stack pointer. So a group of memory locations in a RAM is referred to a stack. In a internal memory, a group of few locations is referred to a stack. So this stack can store data as well as address during execution of program, and it is initialized at 07H location. Okay, at that address it is initialized first. So whenever I reset, it will directly go and point towards 07H location in internal memory of RAM. So see where here on stack, whenever I want to, I can store some data or some address, or else I can retrieve that data and address from the stack. So for that, how the operation works is, before that I said first it will point towards 07H. So after the reset operation the stack pointer is initialized at 07H. Then if I want to store whenever it starts to begin, that means if I want to store, generally the instruction what we use is push, PUSH. Whenever I write that instruction, then I wanted to store onto so and so location. Where it stores is, it automatically from 07, before storing the value, it first increments. Whenever it is trying to store the value on a stack, this sp value, okay, nothing but stack pointer. What does stack pointer mean? To where it is pointing. It initially it was pointing towards this 07h address. So what happens is, first it initialization, it is on reset, it is pointing towards 07. What? sp is nothing but stack pointer. So now whenever I start to store a data on a stack, this sp will increment first. From 07 this will become 08. Okay, after incrementing by 1, then the so and so value is stored on the stack. That means where it does store, if it is pointing towards 08, the value is stored on 08 location. Okay, next, whenever I want to retrieve the value, if I want to retrieve the value from the stack, take the value from the stack, then what it does is, first it will take the value from a stack and then decrement by 1. That means before we stored, so now it is pointing towards 08 location. So there whatever we stored, that value is being taken to so and so address, whatever we have written. After taking, it should decrement by 1. From 8 it will 8 minus 1, so it will decrement by 1 means 8 to 7. So it is pointing again towards 7. So these are the two very important operations used for this stack operations. Okay, for storing you use the instruction called push, and for retrieving you use an instruction called pop, pop. So next you have is data pointer. So this data pointer register is made up of two 8-bit register. Okay, generally this is of 16-bit register, where we can divide it into two ways, that is 2 8-bit. So one is DPL and one is DPH, and it can let me show you how. See here, see, this is complete DPTR register, where DPL and DPH. DPHL is of 8-bit and DPH is of 8-bit. So here this DPL is of lower order from that 16-bit. Next, this DPH is of higher order, data pointer higher, data pointer lower order. So in this way we can, even PC we can write in the same way. This is program counter. Okay, these both are 16-bit registers. PC we can write it in the format of PCH for higher order and PCL for lower order. Yeah, so now we are talking about data pointer. So this function is used to hold the 16-bit address. Now this data pointer is used for addressing the off-chip data and code with two instructions again. Okay, those instructions are MOVX and MOVC. So generally this data pointer is used only when we use some external memory. Whenever we use some external memory, we use data pointer, because external memory has of 16-bit size. So we use this data pointer. So whenever off chip is nothing but external memory. So whenever we use RAM or ROM, we take this. So these are the two instructions for data and code. That means data means RAM, code means ROM. So whenever you use data, generally you write MOVX, MOVX, and whenever you use for code, we write MOVC. C means code here, and X means it refers to external. That's it. Okay, it refers to external. Now after data pointer, you have program status word. See, this program status word, we'll actually know about this in detail when we start in other slides. For now, I can say this is 8-bit register, and this is also called as flag register, because it will show you the status of the operations after you get a result of addition, subtraction or multiplication, okay, or some logical whatever operations you are doing. If you get a result, then whatever flag it is being high or low, that flag status it will be showing in this status word, the program status word. So here you have generally 4 flags, for math operations you have 4 conditional flags. Those are carry flag, then after carry flag you have will come from the lowest order. First you have a parity flag at D0, okay, D0 bit. Next, after parity flag at D2 bit you have overflow flag. Parity flag, it will tell you that whatever the result, depending on the number of ones, okay, if you have odd number of ones, the parity flag will be set to 1, okay, that will be in set condition. Whenever your result is in contains even number of ones, then the flag is in reset condition. Next, after parity you have overflow flag. So overflow flag, this is for like whenever you have you're carrying out your multiplication, okay, when the overflow flag is set if there is a carry from the bit 7th but not from bit 6th, okay, or there is a carry from bit 6th but not from a bit 7th, otherwise it is cleared. What I meant to say here is this overflow flag is set whenever you have a carry from 7th bit or 6th bit. Next I have is, after carry I have auxiliary carry flag. So that is at D6th bit, and carry flag at D7th bit. Auxiliary carry is whenever you have a carry from 3rd bit, nibble, one nibble to the other nibble. Whenever you have a carry in that way, you have this bit as set. Next, carry flag. Whenever you have a carry from 7th bit, then this carry will set, okay. And apart from this you have more one reserved for future purpose, and you have one user flag register, and you have two more registers, two more bits, those are D3 and D4, that is register bank select bit 0, register bank select bit 1, okay. These two bits, why do we use, where do we use, we'll see about that when we talk about the memory, RAM, internal RAM memory. Next you have port 0. Port 0 to 1, 2 and 3. So each latch and corresponding drivers of port 0 to 3 is allotted to the corresponding of chip IO port. So these 4 ports are, it is nothing but used to, those pins are used to interface some devices like LED, LCD, which we already discussed. Next, serial data buffer, 2 independent registers, that is for transmitter and for receiver. So whatever, whenever you are receiving a data from some other place to our 8051, then here that in a buffer you have the received information, okay. Whenever you are trying to transmit, then the transmitter data will be stored in the transmitter buffer. Next, program counter. Now this program counter is a 16-bit register. DPTR is a 16-bit register and program counter is a 16-bit register. And the two timers T0 and T1 are 16-bit timer and counters. Apart from these, maximum all the registers are of 8-bit. So program counter, it is used to hold the address of the next instruction to be fetched. Generally what we say is this PC is automatically incremented to point the next instruction in the program sequence after the execution of current instruction. Whenever there are some 10 lines of instructions in a program, when the 5th line is being executed, then the program counter will be pointing towards the 4th line. So because that need to be fetched next after the completion of the 5th line, after the execution of 5th line, the 4th line need to be executed, right? So this PC, what it does is, in the beforehand itself, it will, sorry, not 4th line, 6th line, when the 5th line is being executed, the PC will have the 6th line. It will point towards the next line, that is the 6th line of a program. So because after the 5th line is been executed, the 6th line should be executed next. So at the time of this being fifth line is being executed, the sixth line is already it points towards this sixth line, so that it will fetch next after the execution of fifth line. So listen this line properly. The PC is automatically incremented to point the next instruction in a program sequence after execution of current instruction. Next you have is after program counter, timing and control. Yeah, we discussed on this also. We just discussed on timing and control unit. It is nothing but it is used this unit is used to synchronize all the operations with the clock and generates clock signal for proper functioning. This oscillator, it generates the basic timing control signal for the operation of circuit using crystal oscillator. Then ALU, even this we saw, it performs 8-bit operations, okay, through this two 8-bit registers, that is temporary registers. Next SFR register bank. Yeah, this SFR lies at a range of 80H to FFH. I said you have SFRs, that means you have accumulator, B register, program counter, then DPTR, PSW, then TMOD, TCON, port 0, port 1, port 2, port 3, all these are in this range only, in this 80H to 0FFH range only. Okay, so all this come under SFR register bank. It can address using their respective addresses. So generally what is the address for A? That is E0. At that location, at that address, this accumulator is been there. Next for B it is F0. Okay, so we'll even see those slides for that. See, this are two 16-bit registers and these are 8-bit registers. This is stack pointer, A accumulator, then B register, and we'll also see what are these are. These are also registers R0, R1, R2, 3, 4, 5, 6 and 7. When we talk about memories, we'll see this. Yes, so this is the 8051 memory organization. In this memory organization, we have internal memory, that is on chip. Internal memory, we can say it as on chip, and off chip memory, that is external memory. So internal you have RAM and ROM, where RAM is also called as data memory and ROM is also called as program memory or code memory. Whereas external memory, also you have RAM and ROM. So the size, we'll see the size of internal RAM and ROM, external RAM and ROM. In internal data memory, in internal RAM, we have 128 bytes. Yeah, in yes, so in internal, the size of internal RAM is 128 bytes, whereas the size of internal ROM is 4 kilobytes. Coming to external memory, the external RAM, it can address up to 64 kilobytes. ROM is also, it can address up to 64 kilobytes. Is that fine? So internal RAM and ROM, external RAM and ROM. This is the memory organization of 8051. Now we'll see in detail about internal RAM. Yes, see, internal and external data memory, that is RAM. So this is 128. Internal RAM 128 bytes 0, that is we write it in the form of hexa, okay, hexadecimal form, that is 00H and 7FH. So the address what we write is in the size of 8-bit because it is having only 128 bytes. Next, from 80H to FFH you have some special function registers, okay, we'll talk about that later. We'll only see about this internal RAM. first, and this is external. For external, it is of 64 kilobytes. So that means you require 16 bit size for writing this address of this, that is 0000H, whereas the ends at FFFFH. Now we are concentrating more on this. We'll see about this. Yes. See, it is starting at 00H and ending at 7FH. So this is internal RAM. The size is of 128 bytes. So the decimal number 128, that is a decimal number. If you convert that to hexadecimal, then you will get this 7FH. Now this internal RAM is divided into three parts. The first part is this part, that is from 00H to 1FH. This part generally it is of 4 banks inside it. Okay. Next, after this, the other part is you have bit addressable register. That starts from 20H and ends at 2FH. Okay, 16-bit addressable registers. That is bit addressable registers. Next, here the last part is general purpose registers. Starts at 30H, ends at 7FH. So this general purpose register is also called as stack register. Scratch pad. Yeah. Now coming to this, actually what are these? So in this internal RAM, at this 00H to 1FH, it is divided into 4 banks. Each bank will again consist of 8 registers inside this bank. That means, see, R0, R1, R2, R3, so on up to R7. Okay, you have total 8 registers inside this bank 0. Now R0 is the register R0 is the size of this R0 is 8-bit. Same way R1 is also 8-bit. So each register is of 8-bit size. That means in bank 0 you have total 8 8-bit registers. If I name them, those are from R0 to R7. Same way I have at bank 1. At this bank 1 I have R0 to R7, same 8 registers. And in bank 1, which each is of 8-bit. Same way at bank 2 I have 8 registers. In bank 3 also I have 8 registers. So out of all these 4 banks, this 8051 by default it uses only bank 0. Is that fine? So this uses only this bank 0, and whenever if I want to use some other bank, I can change that from one bank to another in program status word by selecting the if you remember, I said you will have 2 bits. Okay, for register select bit 0, register select bit 1. If those 2 bits by setting and resetting those bits, I can select any bank from these 4 banks, but by default it has bank 0. And if you observe one more thing, see, at 00H I have R0, at 01H I have R1, at 03H I have R3. So in this way, at 07H I have R7. After 07, next I have 08. So at 08, after R7, the next bank 1 starts. So register R0 of bank 1 is there at 08H location. So when we spoke about the stack pointer, if you remember, try to recollect that it is initialized at 07, I said of internal RAM. So this is internal RAM what we are talking about, 128 bytes. So this is the 07 location, that means bank 0 of R7 register. Initially it points towards this location, that is 07, but whenever I try to store something onto that stack, what it does is it will first increment by 1, then stores the value. So it will increment from this 7 to 8, then the value is stored on 08 location. Then if I want to store some other value, again it will increment from 8 to 9, and the other value will be stored on 09th location, that is R1. So by this I can say, and that is of 8-bit size. I said stack pointer is of 8-bit size. By this I can say that this bank 1 is generally used for that stack pointer operations, to store the values of stack pointer operations. If you are not using the stack pointer operations, you can use it like a normal R0 to R7 bank 1 registers to store any values. And this all the 4 banks can't be used at a time. Simultaneously you can't use all these 4 banks of an internal RAM. You can use one bank at a time. If you are using bank 0, then you can't use one bank 1, 2 and 3. Okay, so if you wanted to change from the default bank 0 to some other bank, to some other register bank, then you can change that by manipulating the bit number D3 and D4 in PSW register. So till here we saw 00H to 1FH. This is completed. Now you have bit addressable registers, that is starts from 20H to 2FH. So from this 20H to 2FH, what is happening is, yes, here from 0 to 2FH, what happens is, this is bit addressable register. So you can manipulate each bit individually. If you are having 1 byte register or 8-bit register, you instead of rewriting or manipulating the complete 8-bit register, you can manipulate 1 bit individually. So here so this is the bit addressable register. If you want to do that, you should always use from 20H location to 2FH locations only. Okay, next I have general purpose register. So for all the general purpose, for whatever operations you are doing, generally you will start to store the results, values. You will try to assign the values from this location only, 30H to 7FH. So this is general purpose register. Generally for our all operations we use this register to save the results, or else to save some input data values, some data and all. So this is internal RAM we have completed. See, after this is only this is internal RAM. Okay, 0H to 7FH. This 128 bytes, and this doesn't come under internal RAM. The upper 28 is written right. This doesn't come under any internal RAM. This is called some special function register. Separately you have from 80H you have different locations where your ports, your data pointer, stack pointer, SBUF, SCON, accumulator, B register, PSW, at this locations they are stored. Before as I said you all, see, accumulator I said E0H, at this location accumulator is there, F0 there is B, and ports are at it starts from 80. Yeah, see, 80 I have port 0, then after that 81, 82, 83, 84, 85, 86, in that way you keep having the addresses, whereas at 80 you have port 0, then 81 you have stack pointer, 82 DPL, data pointer lower bytes, whereas 83H you have data pointer higher bytes, in that way. And port 1 you have at 90H, after 90H port 2 you have at A0H, then port 3 you have at B0H. Okay, so 80, 90, A0, B0, all 4 ports. In this way, at that locations those are being stored. So if you see in more detail of this internal register, these banks and all, see, it is written in this way. This is one part, that is called working registers. You can store in registers also. So this register is named as the name is given to it, as well as we can access using this address. Okay, see, this is the first part. This banks, all 4 banks are there, right? These 4 banks are this part. Start from 00, ends at 1FH, this bank area, nothing but we can also call it as working registers. So see, it starts at 00H location and ends at 1F. So inside this what you have is, see, the R0 of bank 0, it is at 00. Next R1 of bank 0, it is at 01H. R2 of bank 0 you have at 02H. Same way, so on. R7 of bank 0 is at 07H. After 07 you will have 08, 09, 0A, 0B, C, D, E, F. In that way it keeps on going. So if you say bank 1, see, these registers are at so and so locations, 08 to 0F. 08 to 0F of bank 1. Bank 2 starts at 10 and ends at 17. Same way bank 3 starts at 18 and ends at 1F. Same thing he has mentioned in this also. 00H to 07 bank 0, 08 to 0F bank 1, 10H to 17H bank 2, 18H to 1FH is bank 3. That is what he mentioned, the working registers. So see this, if you take bank 0 of register R2 of bank 0, that is at which location? 02 location. So I can use this location in two ways, either by its name or else by its address. So if I use it by its name, I can say R2. Okay, if I use it by its address, I can say 02H. So I can use this location by using its name or else its address. Is that fine? So it is same like, if I give an example, it is same like if you have you have your house, your home. Okay, everyone has a home where the home has some address at so and so location, at with so and so house number it is there, and they also give some name to the house, like so and so Nivas, so and so Nilayam, in that way. So the house can be named, it can be taken as it can be called using its name or its address. So anything, but the place is same, place don't change, the location doesn't change. That is what I am trying to say here. This location can be used by taking its name as R2 or 02. If you take R5, see, you can call it as 05 as an address, or else name if you take, you can call it as R5. So after that, next we will see bit addressable area. See, bit addressable registers are start from 20H to 2FH. So see, it starts from 20 to 2FH, and I said these are bit addressable. So at 20, see, this is 00 is 1 bit, 0 again, after 00 you will be having here 01, 02, next 03, 04, 05, 06, and this is 07. After 07, the next 21 it starts. In 21 you will again have starts from 08. So 08, 09. After 09 you will have 0A, B, C, D, E, F. After F, again it will start from 10. In that way, each bit you can address. You can manipulate each bit individually. This is bit addressable area. Next, the last is general purpose, that starts from 30H, ends at 7FH. So see, this is general purpose area is starting from 30 ending at 7FH. Okay, so in detail if we see, you get that. So these are all 8-bit registers: stack pointer, accumulator, B register, then R0, R1, R2, R3, R4, R5, R6, R7. So by default, if you are using this registers will be of bank 0. If you are selecting B0, bank 1 or bank 2 or bank 3, in that way you need to select at PSW. Whatever you are selecting, that bank's registers will be this R0 to R7. And see, these are those special function registers, the memory where it is the location where they are stored. Accumulator is at E0, B is at F0, where I just showed you. See, 82 means it is DPL, nothing but it is pointing towards some external memory. When will you use this DPTR? Whenever there is some external memory, this DPTR will point towards the address of that external memory. Okay, that means it is having 82 is lower order of that external memory, 83 is the address of the lower order of that external memory. IE is interrupt enable, interrupt priority. So this we'll see whenever we learn about the special function registers. Yeah, now port 0 to 3, see 8090 A0 B0. PSW is at D0. Stack pointer is at 81H. See, don't get confused. This the stack pointer where it is located is 81H, but the stack pointer where it points, that means in 81, inside this 81 where it is pointing, that address will be there. So by default it is initialized at 07 location, that you don't forget. Okay, that is 07 location. And these are the timers. Okay, timer controllers, these things. So we'll see how these banks are selected. See, this is program status word. In this program status word, each you have total 8 bits. Parity flag, this is user defined flag, this is overflow flag. See, this both RS0 and RS1, this both bits will decide, which bank to be selected. Okay, so this RS0 is register bank select bit 0, RS1 is register bank select bit 1. And next you have, this is general purpose status flag, auxiliary carry flag, carry flag. These are the different flags. So in this register, this is also called as flag register because it has 4 flags. See, this is parity is 1 flag, overflow is 1 flag, then auxiliary carry is 1 flag, carry is 1 flag. 4 flags, it has 4 flags, and 2 register bank selectors because these 2 are there. Okay, and this is for user defined, and this is for general purpose, nothing but for future use, normal flag. So this 2, how the bank is selected means, if I take this both, see PSW.3, PSW.4, see if I place 0 in the place of RS0 and if I place 0 in the place of RS1, both as 0 and 0, then bank 0 will be selected by default. Next, in case if I place 1 in the if I set this D3 bit, if I place 1 here and if I have 0 in this D4th bit, then bank 1 will be selected. And now when I have this D4 as 1 and D3 as 0, then bank 2 will be selected. And when I have D3 as 1 and D4 as 1, both as 1, then bank 3 will be selected. In this way, these banks are selected: bank 0, bank 1, bank 2 and bank 3. Depending on that, whatever register we are taking, by default that register location will be of so and so banks. Okay, so about this program status word we will see in more detail in the next video. So by this we'll end this session. So today whatever we saw was, it was all about the functional block diagram and the details of each block in this functional block diagram. It is very easy to remember this functional block diagram because you already know how many pins are there in this 8051 and what are the different functions of each block. So when you learn this, it is very easy to draw this diagram. Next, we saw in detail of all these blocks. Next we saw the memory. The memory organization, you have internal and external. So we saw internal and external RAM. So within this external RAM, you just need to store the data, whatever if you require more in this you will just store. In the same way, if you have some external ROM, see it is in the form of same way. External ROM start from 000H to ends with FFFH, external ROM. If you talk about internal ROM, the size is not same. See, for external RAM and ROM, size is same, 64 kilobytes. But for internal ROM, you have 4 kilobytes. So convert that 4 to hexadecimal. What you will get? You will get 0FFFH. That means internal ROM I am talking about. It starts at 0000H and ends at this will become 0, not 4 F's. You will have only 3 F's there. That means the first F will become 0, then FFFH. Is that fine? That this is about external ROM, and we have seen about internal ROM in detail. and we just saw this bits RS1 and RS0, 2 bits from program status word, how these banks are selected. We got to know this. So in the next class we will see in detail about this program status word and other functions, other special functions, registers. So by this I will end the class. Thank you.